Another statement of Pascal's law is as follows. The change in pressure that is applied to a stationary fluid that is within a container is transmitted without change to every point of the fluid, and to the walls of the container. This means that if the pressure at any point within a stationary connected fluid is increased, the pressure throughout the fluid will increase by the same amount, and vice versa. Consider the situation where we have a piston with a cross-sectional area A1 that is supporting the car. The total weight of the large piston and of the car on top of it is equal to F1. The piston operates on top of a container that is filled with a fluid with density ρ. The container is connected to another smaller piston that has a cross-sectional area A2 and a weight F2. Initially, the system is at equilibrium and is hence stationary. We consider points C and D that are located at the bottoms of columns 1 and 2 respectively. Since both points are at the same elevation and within the same connected body of fluid, the pressure at point C is equal to the pressure at point D. The pressure at point C is equal to the pressure that the car and piston are exerting above column 1, or P1, plus the pressure that the column of fluid above point C exerts, which is equal to the density of the fluid ρ, times the gravitational acceleration g, times the height of the fluid column above point C, or H1. P1 can also be written in terms of the force F1 that the piston and car exert, divided by the surface area of the bottom of piston 1 that is in contact with the fluid, or A1. Similarly, we can calculate the pressure at point D to be equal to the force exerted by the small piston, or F2, divided by A2, plus ρ, times G, times H2. We can then set the two expressions that we obtained for the pressure at points C and D equal to each other. The shown hydraulic system, as we have mentioned previously, is in equilibrium. If a man, with weight W, steps onto the smaller piston, this will increase the pressure that is acting on the smaller piston, and consequently the small piston will tend to move downwards, while the large piston moves upward until a new equilibrium position is reached. To obtain the new equilibrium positions of the small and large pistons, we need to determine the distances that both pistons have moved, or delta x1 and delta x2. Using Pascal's law, we can still state that the pressure at points C and D is the same. We can then write the expressions for PC and PD similarly to what we did before. The shown equation takes into account the fact that the force acting on the small piston has increased by the weight of the man, or W, and that H1 has increased by delta x1, and H2 has decreased by delta x2. Since we assume the fluid is incompressible, then the total volume of fluid within the container remains constant. Hence, using conservation of volume, we can state that the increase in volume in column 1, or delta x1 times A1, is equal to the decrease in volume in column 2, or delta x2 times A2. We can then rearrange this expression to obtain an equation for delta x1 as a function of delta x2, A1 and A2. Substituting the delta x1 equation into the previously obtained pressure equation, we get the shown expression. By rearranging the terms, we can get the following expression for delta x2. Hydraulic power is used in numerous applications as a force multiplier, where a relatively small force can be used to generate a much larger one. One application is that of a braking system on a car. When a driver presses the brake pedal on a car, the brake fluid within a small diameter master cylinder is compressed. This causes the much larger slave cylinder that is connected to the brake pads to exert the high force on the car's brake disc, which tends to slow the tire's rotation. Let's watch this animation a few more times. Pay attention to the brake pads. See how they move slowly together to grip the brake disc. The pressure in a typical car brake system can reach about 10 megapascal, or about 100 atmospheres. Hydraulic power is also used to drive the actuator pistons of various machinery, such as earth-moving equipment. The control surfaces of many aircraft are also controlled using hydraulic actuators. The hydraulic pressure in these applications reaches about 30 megapascal, or about 300 atmospheres. Another application of hydraulic power is in hydraulic presses that are used in metal forming and cutting operations, and in test equipment that is used to measure the strength of material samples. In these applications, the hydraulic pressure can reach 1000 megapascal, or about 10,000 atmospheres. The barometer is a device that is used to measure the atmospheric pressure. It was invented by Evangelista Torricelli, who was an Italian physicist born in 1608. It is made of a glass tube that is filled with mercury. The tube is then inverted into a mercury basin. It is observed that the mercury falls from the tube as it is being inverted, until the height of the mercury column in the tube is equal to 76 centimeters, 4.76 meters. Make sure that no air enters into the tube while it is being inverted. This is to ensure that an absolute vacuum exists above the mercury in the tube, or in other words, that the pressure above the mercury in the tube is equal to zero. We consider point A, which is located on the surface of the mercury basin, and point B, which is located within the tube, and at the same level as point A. According to Pascal's law, the pressure at points A and B is the same. Since point A is at the surface of the mercury basin, the pressure at point A is simply the ambient atmospheric pressure. Due to the near vacuum above the column of mercury in the tube, the pressure above the column is nearly zero. It is not exactly zero, however, since mercury has a very small vapor pressure at room temperature. But this can be neglected. The pressure at point B is equal to the density of mercury, rho m, times the gravitational acceleration, g, times the height of the mercury column, h. Since the pressure at points A and B is the same, then the atmospheric pressure is equal to the density of the liquid times the gravitational acceleration times the height. Using a mercury density of 13,600 kilograms per meter cubed, and substituting 9.84 g, and substituting 0.76 meters for the column's height, we get a value of 101.3 times 10 to the power 3, or 101.3 kilopascal. This is equal to the atmospheric pressure at point A. Hence 1 standard atmosphere is equal to 101.3 kilopascal. Other pressure units that are equivalent to 1 atmosphere are 1 bar, 1 torr, or 760 millimeters of mercury. Note that the torr pressure units were named in honor of Torricelli. If water were the liquid in a barometer, then how high would be the column of liquid that measures 1 atmosphere? And why do you think mercury, and not water, is the liquid of choice for use in barometers? First, let's find the value of H that represents 1 atmosphere of water. As we have seen before, according to Pascal's law, the pressure at points A and B is the same. Hence, neglecting the vapor pressure of water that is acting at the top of column B, the atmospheric pressure acting on point A is equal to the density of water times the gravitational acceleration times the height of the water column above point B. By rearranging the equation, we get that H is equal to the atmospheric pressure divided by the density of water times the gravitational acceleration. Now substituting in the values of the variables: 101,300 for the atmospheric pressure, 1,000 kilograms per meter cubed for the density of water, and 9.84 g. We get that the height of the water column to measure atmospheric pressure in a water barometer would be equal to 10.3 meters. There are two reasons why mercury, and not water, is used in barometer. First, due to the high density of mercury, a much shorter tube can be used. The height of a column of water to measure atmospheric pressure in a barometer is, as we have just calculated, 10.3 meters. Whereas in the case of mercury, a much shorter column height of 0.76 meters is needed, which is a factor of 13.3 times smaller. Furthermore, the vapor pressure of mercury at ambient temperature is much lower than the vapor pressure of water at ambient temperature. With any liquid that is used in the manometer, the space above the liquid in the tube will always be filled with the vapor of that liquid at a pressure that is equal to the vapor pressure of that liquid at that temperature. Hence the assumption of a vacuum above the liquid in the manometer tube would introduce a small error into the measurement of atmospheric pressure, depending on the value of the vapor pressure of the liquid that is used in the manometer. The vapor pressure of water at 25 degrees Celsius is about 3 kPa, which would introduce an error of about 3% into the atmospheric pressure measurement. In contrast, the vapor pressure of mercury at the same temperature is only about 0.2 kPa, a factor of 15 times smaller.